Thank you.
Our next company, which is showcasing their product today, is Microchip Technology. Microchip Technology is a leading provider of smart, connected, and secure embedded control solutions. The company's solutions serve more than 120,000 customers across the industrial, automotive, consumer, aerospace, and defense, communication, and computing markets. Its headquarters in Chandler, Arizona, Microchip offers outstanding technical support along with dependable delivery and quality. Today with us, we have Mr. Deeptesh Nandi. He is a product marketing manager in Microchip's FPGA business unit. He leads worldwide technical marketing activities for smart embedded vision and Vectorblocks AI for Polar Fire FPGAs. Hi, Mr. Deeptesh. Request you to take over.
All right. Thank you so much for the introduction. Let me go ahead and share my screen. Is my voice clear? Is it audible?
Yes, it's audible.
All right. Thank you. All right. So can you confirm that you can see the screen? Is my screen visible?
Not yet.
Oh, just a second. Let me try again. Yeah, is it visible now?
Yes, it is.
All right. Thank you so much. Yeah. So good afternoon, everyone. My name is Deeptesh Nandi. I'm part of the marketing team in the FPGA business unit for Microchip. And in today's discussion, we're just going to go over very briefly how do we sort of define and design a small form factor sort of anti-tamper fanless AI machine learning algorithm using FPGAs. So we've heard our previous speaker talk about ASICs. There was, I believe, a presentation before with another FPGA. For Microchip's point of view, our FPGAs are extremely small form factor, extremely low power, and we target AI inference applications that demand the requirement of having extremely small power consumption and many other features. So we're going to basically go over at a high level what those challenges are that our customers typically sort of come up to us with. So we are really extremely successful in the smart embedded vision areas, which demand sort of extremely small form factor solutions that do not have a lot of space to sort of include a thermal fan or a heat sink, but they also require higher resolutions. I mean, they're not happy with 1080p resolutions anymore. They want to go towards 4K. They want to sort of target 8K kind of resolutions. And when you drive systems at that high speeds, and essentially because FPGAs have high-speed transceivers that enable you to drive those high bandwidth requirements, power is a extremely tangible concern that faces our developers. Security, again, it was mentioned in the previous presentation. Security has been important, especially in edge applications, because they're typically deployed outside the purview of the traditional physical security. You do not have any guards or barriers protecting your installations in automotive, in remote installations, maybe in drones. So you want to ensure that let's say a drone crashes and it gets into a hand of someone else, your IP that you use to sort of implement the drone system, the image processing, everything is protected and it's not easily hacked or extracted. So our objective today is the following. I mean, we're trying to get an FPGA, a traditional FPGA, to essentially run a machine learning algorithm to sort of um, come to a solution that is more applicable towards the edge. We're going to see how different problems with respect to power, with respect to changing environments, make it absolutely essential, at least for the first build of customers, for them to at least start their prototyping with an FPGA platform. Not going to spend a lot of time over here. I think what we're trying to say is that whenever we are talking about inference, there are 2 or 3 things that are extremely important. The need for inference on the edge is driven by the need for latency. And because edge systems do not have the kind of power and performance that is required to, which is typically necessary for traditional AI and ML algorithms, you need to have essentially some features that enable your algorithms to be able to sort of, first of all, convert into lower resolutions, and that is essentially something what we call as model conversion and model processing before they can be deployed into edge devices. So power and space are constrained in embedded devices, and obviously we talked about how it needs to be secure as well as reliable, because often installations might be completely outside the purview of general security. So let's talk about power. It essentially becomes important to have a thermally cooled system whenever your system power goes beyond 5 watts. That is when we've seen customers actually come to us and talk about the requirement of a heat sink or a requirement of a thermal fan to essentially cool the system down. While some of this can still be sort of mitigated for certain applications, maybe like a drone. But if you talk about portable medical devices, let's say endoscope camera, which is looking to sort of increase the resolution from a traditional 1080p to like a 4K resolution. If you do not control power, you cannot actually put that device into an invasive sort of medical instrument. And in an invasive medical instrument, the size of the instrument is at a premium. You cannot really put heat sinks or thermal fans. And then when you try to drive a 4K image processing workload, it becomes extremely important to ensure that the power is controlled. And then your system also has the additional bandwidth to run AI algorithms. So power does not only mean battery life, it means heat dissipation. In thermal imaging cameras, for example, the stray heat near the enclosure will cause interference, and the image quality will get degraded. And in order to get rid of those image degradation, you might have to sort of implement additional ISPs. So if you have a lower power chip, a lower power FPGA that is immune to sort of high energy temperature spikes, that really solves the customer's problem. Functional safety is becoming extremely important, not only in industrial, but also in automotive. Suppose you implement a very simple design like this, where your camera is interfacing with, let's say, a receiver, can be MIPI CSI, can be LVDS, can be SLVSCC, and then you do run different processes of dumping the data out into DDR and then doing some image processing, doing scalar applications, color space conversions, and finally getting it ready for an AI engine to basically run itself and provide inference results. And then maybe at the end of it, you want to essentially merge the inference results with respect to drawing boxes or text to the original image, which was captured from the frame, and then sort of dump it out through a display, dump it out to another ECU in an ADAS. And essentially what we're trying to do in this case can become extremely difficult, let's say, if you are trying to make a safe design. Now systems can fail because of processes. Systems can fail because of random events. There might be transient events where, let's say, a bit flips in causing a soft error that needs to be mitigated. So in order to make the systems, really critical systems, operate in an automotive or an industrial kind of applications, we do have to ensure that the embedded processors follow the industrial functional safety, as well as ISO 26262 for automotive, thereby essentially ensuring that at every stage of a image processing function or an AI function, you are able to detect errors up to a certain level, correct some of the errors also. But essentially, if anything goes wrong, let's say during the MIPI CSI receive cycle, maybe a link gets corrupted, or maybe CRC fails, you need to be able to know that something has gone wrong. And if you can correct it, that's fine. If you can't correct it, you let the ECU know that, hey, let's not use the input from the camera because there might be something wrong. So it becomes important for embedded processors to have, for example, ECC, SegDet, single error correct, double error detect functionalities. Some memory controllers might not support ECC. You might have to create inline ECC to sort of enable error correction codes. You need to ensure that your soft processor or hard processors, the cache is monitored right through flush and have another ECC functionality. So there is a lot more that goes into creating a safe design, and that needs to be sort of provided through industrial and automotive functional safety. That also becomes extremely important for an edge embedded design. The third challenge is what we've seen are evolving requirements. AI is, I believe, there's a long way to go before it becomes saturated. It's still what I would say classify as a nascent sort of market where more and more customers are evaluating it, figuring out what works for them, what are the flows that are important to them. And what we've seen is that algorithms will change and can change from time to time, not only during prototyping, but also in production. So your system has to be smart enough to support online updates, over-the-air updates. Your image processing techniques can change, your compression techniques can change, and then your network interfaces can change. You might choose to use HDMI output for prototyping, but eventually you might end up using an Ethernet interface or maybe a co-express interface, who knows. So we have had customers having a multiple options of using different interfaces as per their device requirements. So a challenge is to be able to enable flexible designs in AI today as well. Security is something that is coming up right now. I think originally we did not have a lot of customers who were interested in security, but suddenly there's a spike. And whenever we talk to our customers about security, they are interested in learning more. They are interested in learning how different vendors, for example, use different techniques for the challenge of security. According to me, there are like 2 or 3 points for security that we need to ensure. First of all is, can you protect your device from running unauthenticated code? If someone hacks into your system, someone hacks the non-volatile storage where you're maybe storing your weights of the neural network. What happens if unknown code is being sort of somehow maliciously put there? That's number one. Number two is, what happens if somehow your code is being extracted because a customer can buy, a person can buy a device on the market. They can use many techniques to sort of take out the IP that you've developed. And number three, what happens if you have taken out the IP? Can you, for example, create a sort of duplicate part with original FPGAs, by the way, with the same FPGAs, but from a different vendor, because it becomes aftermarket, and then program the FPGAs or embedded processor using the extracted IP. So there's 3 different processes, and there are many ways in which the companies provide these features. For example, Microchip's FPGAs have protection against side channel hacking. There have been absolutely no reports of any hacks that have happened due to differential power analysis. We are licensed by the Rambus Cryptographic Research Institute. We have womb to tomb kind of security. Essentially, you can identify every die because we put in private keys at the time of wafer manufacturing, and you can use those IDs. So even if something happens, someone extracts your IP, they cannot actually program the IP if, let's say, they have a tie-up with your system vendor or your contract manufacturer, because you control the number of devices that gets programmed, you control the number of FPGAs that gets programmed, not one FPGA more or less. Finally, how do you ensure that your IP does not get extracted from an embedded chip? There are many ways to do it. We do it by providing anti-tamper mechanisms. We monitor clocks, we monitor temperature, we monitor IOs within the chip, and we provide an API to sort of provide the customer different ways to mitigate it once those hacking conditions are sort of determined. Reliability is, I mean, it was primarily due to software errors creeping up in applications today. Reliability was most used originally in the avionics space, where there is a high chance of stray radiation particles hitting a fabric. The fabric can be based on SRAM, it can be based on a flash, where your configuration files are stored. Again, reliability can sort of depend on various areas. You can corrupt the memory, which the system is reading again and again. You can corrupt the logic, which can potentially change the system functionality altogether. And you can change the flip-flops. Flip-flops, probably integrated logic, can be slightly easier to correct, but there are ways where a software can completely destroy the functionality that you have integrated in your system. And the way to solve this is, like I said before, you implement single error correct, double error detect mechanisms. You ensure that all the memories within your architecture is protected. You ensure that if you are not protected, you implement triple module redundancy protocols. And maybe if you use a non-volatile flash-based configuration like polar fire FPGAs, you are completely immune from the start because of the architecture. So we talked about the different challenges. Let me give you a reason why FPGAs are still being used for AI and ML today. It's still a nascent market, and because of the reasons I mentioned before, because the requirements keep on changing so many times, FPGAs just offer you the best way to sort of implement all your requirements through programmable IP. And Vectorblocks is our machine learning inference IP. It's part of the AI and ML sort of offering that is associated with our FPGA offerings as well. So Vectorblocks is here. It is essentially inference IP. Like most of the IPs that you've seen in the market, most of the solutions you've seen in the market, it is configurable. It can be configured for different performance ranges. Based on configuration, it will basically use up more resources or less resources. It has a software overlay. I'm going to talk about this very briefly there as well. But our differentiation comes from power consumption. The top 3 lines are our examples of how we configure the IP, the Vectorblocks IP that can deliver as small as 80 gigaops, as high as 280 gigaops, can go up to 1 teraops, depending on configurations that you choose. And I'm comparing it with a competitive FPGA that we see in the market as well. So if we take just the 2 rows over here, we are essentially outputting a similar giga operations per second number. But once you look at the total power consumption, it is almost 30% lower, 60% lower than the competition. So 4 watts versus 1.3 watts for similar ML output. So this is also referenced under this block and this block. So what we are essentially trying to focus is on applications that require low power consumption. They need smaller enclosures and fanless designs. You cannot put heat sinks, you cannot put thermal fans, because that's the overall requirement of your end customer. And we offer our ML solutions to be at least 2 to 3 times more power efficient in terms of giga operations performance per milliwatt. So that's really our niche where we are successful. Quickly on Vectorblocks, I think the main goal for Vectorblocks is to enable software developers, as they are the ones who are most likely to be evaluating neural network solutions for your customer, for you as well as your designs. So essentially, it enables software developers to start evaluating the solution without requiring any FPGA design expertise. It's a software overlay method where we provide the initial FPGA hardware design, and using the software the software SDK, it becomes a plug and play kind of an application where they can change around different neural networks, they can change the functionality of the neural networks, and so on and so forth. What we also provide is a bit accurate simulator. So even to get started, you do not even require a hardware to get your workflow started. You can just download the SDK, start hooking up your CNNs or our CNNs from the demo files, from the networks that we provide, and basically start seeing the performance, start looking at the simulator outputs, the design bandwidth, the DDR bandwidth, the latency numbers, all are sort of provided at the simulator level. If you think that matches your requirements, then only you need to sort of come back to us, maybe get a hardware kit, and then start seeing how actually the simulation results match the final performance. Not going to go into detail. This is what I meant by a software overlay method. Traditional FPGA flows, you start with creating an RTL. That's where hardware designers are required. You synthesize the RTL, then you place and route, and finally you program the FPGA. With Vectorblocks, we provide the neural network engine IP. I believe that's what most of FPGA vendors also provide. That enables the software developers to really work on the C++ based development and neural networks that are converted to an accelerator. So they are completely spared this hardware flow, which typically is expertise for a hardware engineer. Again, I think this was covered in the previous presentation, so I guess you see and know what it means. What I just wanted to convey is how we sort of come up with power numbers. A typical facial recognition algorithm has 2 CNNs at a minimum. The first CNN sort of identifies the heads in a video frame, and the second CNN basically landmarks those video images. And that's how a typical facial recognition algorithm works. So in an FPGA, you do get to implement the complete solution from image sensor interface to the last end output. And you see the performance numbers. While you get the performance number, you do also see the power numbers, which is like extremely small, 1.2 watts to implement the facial recognition.
We are falling short of time.
Yeah. So this is my last slide.
Okay.
So this talks about what we have available today. I've given the links below for if you're interested. All our software development kit are available in GitHub, free to download. And you can get more information on the website with respect to what hardware is supported and what are the example projects we support today. Everything is free to use, everything is free to evaluate. And we have many sort of tutorials to help you get started with your designs. So that's all I had. I probably exceeded my time, so apologize for that. If you have any questions, I'll be glad to respond. Otherwise, feel free to reach out to me over emails.
Thank you, Mr. Nandi. It was really an informative session. In the paucity of time, we would like to ask you only one question, which is from the audience. Can Vectorblocks support multiple CNNs?
Yes, Vectorblocks can support multiple CNNs. The way we do it today is by time slicing. Essentially, CNN1, CNN2, CNN3 can be switched instantaneously. So if you can afford to wait like milliseconds where the CNNs can be switched, and that is how fast the CNNs are switched, then you can realize the same function. But if you want multiple support, that is also available today.
Thank you so much. Thank you for your time.
Thank you.